In the last video, I mentioned that the key thing to remember about magnetic fields is that the source of all magnetic fields are currents. They may be microscopic atomic currents, or they may be macroscopic currents in an electric circuit, but all magnetic fields are created by moving charges, i.e. currents. Ampere's law describes how to determine a magnetic field for a current, provided that there's a certain amount of symmetry. In more advanced courses, calculus-based courses, and upper-level physics courses, one develops a more generalized result from Ampere's law called the Biot-Savart law that will work for very small pieces of wires or moving charge, but it is much more complicated. Ampere's law reminds us a lot like Gauss's law. It requires us to know certain things, but when we know them, we're able to solve some important problems in very, very slick and easy mathematics. Here's what Ampere's law says. Take in space a curve. The curve can be any curve that you want. Let's take a curve like this. And along that curve, at each point, there's some small amount of dl, a little bit of length. dl, a small amount of length. And we can think about breaking this curve into small lengths all the way around the curve. Each one of these having a small delta L at that point of the curve. Now, the curve binds, or bounds, I should say, a region. You can think of it like a drum head. Now, this is one of the really weird things. We're going to find that Ampere's law says that what goes along the rim of the curve is impacted, or connected, if you would, to what's going on in this drum head, this piece of material that's being attached to this little outer ring. Now that seems kind of strange because the point here wouldn't seem to have anything to do with the point over there in space. But again, if you think of it as a drum head or other little piece of cloth, how tight you pull down, say, on a sheet impacts how tight it is in the middle. Even though you're not pushing in the middle, you're pulling on the edges. So the edges through the sheet impact. This thing is saying that not just for a material sheet, but for space itself, this point along this edge will impact that thing in the middle, and vice versa. Now, next thing about Ampere's law. It says if there's a current that penetrates, maybe it's a wire like this, going through here, and it's got some current going up. Maybe that current is 2 amps. And maybe there's another current over here going down. Maybe that's 1 amp. That there is a connection between these currents and the magnetic field along this curve. So let's take this point here. Let's say that there's a magnetic field like that. And we have a small piece of the path, delta L, like this. And there is some angle between those two, right here. If you take B, the strength of the magnetic field, and the small length, delta L, and you take the cosine of the angle, that is, if you find out how much of B lies in the direction of the red arrow, and if you were to sum that up all the way around this green curve, you would get a number. This is on a closed curve. Maybe that number is 12, but you would get some number. What we find out is that number is equal to mu naught, the permeability of free space, times the total current that penetrates the sheet bound by that. In this case, mu naught times 2 amps going up, 1 amp going down. So it'd be 1 amp. 2 amps minus 1 amp. Now you might ask, how do I know if it's plus or minus? If you wrap your fingers of your right hand in the direction around the loop, your thumb is pointing the direction of the positive current, which in this case would be up. This is called Ampere's Law. Let me write it here. The sum of the magnetic field that's parallel to delta L is equal to the sum of B times delta L times the cosine of theta is mu naught times I penetrate. What I generally call just I sub P. Penetrates this blue sheet. This must be over any closed path. It does not matter the shape of the closed path. If you change the shape of the path, you'll change the blue sheet. So let me show you kind of how this works. Let's say that we had a current of 3 amps coming here and 2 amps coming there and 1 amp going into the screen, and you asked me to calculate the integral for this curve. Integral, I should say sum, for this curve. The sum of B parallel delta L would equal 3 plus 2 is 1. I'm sorry, 3 plus 2 minus 1 mu naught. 4 mu naught. 4 amps times the value of mu naught, 4 pi times 10 to the minus 7. If you wanted to take some different curve, that curve, the sum of B parallel delta L would be equal to mu naught. So I can find this sum relatively easy. All I have to do is add up the currents. That's not what I really want, though. What I really want is to find the value of B. I want to find the magnetic field for certain special problems. For this to be useful, I need to be able to find the way to get this B outside of the sum. Now, there's two things I want to do. One, I want to make this cosine theta, which is part of this B parallel, I want to make that equal to 1. That is, I want to choose a path where the delta L's and the B's are lined up. In other words, I need to know the way the field lines look so I can draw my curve along them. How could I do that? Well, I could map the field lines with a compass, or I could map them with iron filings, or what usually happens is it's some special problem that is well known. The second thing is, besides making the cosine of theta equal to 1, I want to map it so that along that path the B is constant. Again, I want to map along the B field lines. If I can do that, the B can come outside. The cosine of theta will be 1, and I simply have the sum of delta L, which is the length of the path. So, if I have a system of special symmetry in which I know the shape of the field lines, Ampere's law can be used to find the B field. And in that case, that special case, B times the length, L, is equal to mu naught times IP. Special case. But every problem that we want to work is one of these cases. L is simply the length of the path. B is the magnetic field that I want to find. IP is the amount of current penetrating the sheet, and mu naught is the permeability of free space. In the next set of videos, we're going to do some very special cases where we're going to look at using this to solve for the B field. I'll see you in those other videos.